Jonah Flint, and this is my Physics 2212 Lab 4 report. So in this lab, we're trying to predict the behavior of simple circuits, examine the behavior of ohmic resistors and capacitors, and compare our experimental and calculated values. Just a quick overview of our findings. We found that the current for a two resistor circuit was about 0.02 amps. And that the calculated and experimental currents and potential differences did match very consistently, and our RC time constant was 5.984 seconds. Some key concepts: we have the node rule, which is that the current in is always equal to the current out, the loop rule, which is that the change in potential for a round trip is always 0, then resistance V equals IR, and then we have our equation for capacitance here, and finally the equivalent resistance equation. In part 1 here, we're just finding the predicted and the actual current for this simple circuit here with two batteries, both in series, both 1.5 volts. We have two resistors, one is 47 ohms and one is 100 ohms, and we found that it has 2 amps. We predicted that the current was 0.0204 amps, and we found that the actual current was 0.02 amps. And we found that the reserved ammeter found that there was negative 0.02 amps, and the negative is just due to the direction of current into the ammeter. In part 2, we are using the same circuit as number 1, but this circuit is open here, and we are taking a voltage reading across that gap. And we found that we predicted that the potential difference was 3 volts, and there was no current. And that is what we found experimentally as well. This makes sense because there is a gap in the circuit, so obviously there can be no current. Part 3, we are finding the potential difference around a circuit here, this given circuit, and it's the same as circuit 2, only this time it is closed, and then we measured at all these different points across here. A to B was 3 volts, B to C was 0, C to D was negative 0.96, D to E was 0, E to F was negative 2.04, F to G was 0, G to H was 0, and H to A was 0, and these are all consistent with the loop rule. Part 4, we have an ammeter in parallel. So this ammeter is in parallel with a 100 ohm resistor, and the current measured by the ammeter increased from negative 0.2 to negative 0.6, and this is consistent with our mathematical model down here. In part 5, we are calculating the resistances. To do this, we are just using our V equals IR here, and we're comparing that with our experimental model. We found that the resistor across the 47 ohm resistor was actually 48 ohms, the resistor across 100 ohm resistor was 102 ohms, and the ammeter and wire were both 0 ohms, approximately. In part 6, we are examining an RC circuit, which is a resistor and capacitor, in this case a resistor being a light bulb. We're first constructing the RC circuit, then we are measuring the time to charge and discharge the capacitor in the circuit, and then we're going to repeat with a different resistance in the light bulb. We found that the 10 ohm resistor had a charge time of 15.4 seconds and 15.2 seconds to discharge, and then when it was 20 ohms, it was 25.9 seconds to charge and 27.5 to discharge. Generally, more resistance means more charge and discharge time. In part 7, we are finding the time constant here. And to do this, we are basically just removing the battery and pausing the circuit at 1 second intervals to gather the potential difference for each second. And then we can plot the V over V naught versus time graph and find that, or the time constant is then 1 over the slope of that line, and then we find that the time constant is 5.984 seconds. For discussion, generally we found that calculated resistances are greater than the actuals. And possible sources of error are lack of precision in the ammeter, in that it only goes to 2 decimal places. There could have been some rounding in my calculations, and the time error or some timing error for the charge and discharge times. For the what if we used a real ammeter instead of an ideal ammeter? In that case, we'd have a non-zero resistance, and we'd also have a decrease in the current in the circuit, and thus the ammeter would read that difference. And then what if we used a real battery to charge up a real capacitor with no resistor? Well, the ideal model would say that the capacitor, the model says the capacitor charge within 1 second, but this cannot be true because we know that the wires and the capacitors both have non-zero resistance. Thank you very much.